Okay, so what we're trying to do in this video is show that integer programming is NP-hard using set packing. And anytime you're trying to prove or try to find out if a certain type of algorithm is NP-hard, what we have to do is we take an existing thing that we know is NP-hard and we use it to compare it with the one we're trying to figure out. And so kind of a formal way to write this is we want to show that set packing, this is the problem that we know is NP-hard for sure. We want to show using reduction that integer programming is as hard or harder than set packing. So if we know set packing is NP-hard, then, and this is true, then integer programming is NP-hard as well. And so, yeah, kind of like what I said, this is called a reduction. We're reducing set packing to an instance of integer programming. And you might be like, what the heck is this little p? What does that mean? It just means that we're able to translate all possible instances of set packing to a specific instance of integer programming using a polynomial algorithm. And oh my gosh, I was once I saw this diagram, it all kind of clicked for me, so I'm gonna redraw it. Pretend these two circles are the same size. Maybe I'll use a color to help show that these are the same thing. Okay, so given that this can represent set packing, we want to show that for any type of set packing problem, we can map its inputs to a specific instance of integer programming. But yeah, basically if we're able to map this using a polynomial translation algorithm, then we know that integer must be at least as hard as set packing, because there's this little nugget within that we know is going to be NP-hard. So in order to do integer programming, it must be NP-hard as well. So the reason why this diagram was so helpful for me was sometimes I was trying to think about integer programming first and how does it relate to set packing. You can have other instances of integer programming that isn't necessarily in set packing. So it's much better to think about set packing first and then try to translate that to integer programming. So that's a really good structure in general when you're trying to do these problems. Okay, so let's show that integer programming is more hard. So what's important is, what are the inputs for set packing? Okay, let's just write out inputs for set packing, and that'll later help us think of some inputs for integer programming. So for set packing, we're normally given a universal set, and I'll just call this U, and it's going to contain some elements in there. I'm just generating some for an example, and then we're also given subsets as well. Again, I'm just generating some random subsets. They can really be anything. Let's do B, C, and then let's have a third one for fun. We have D. Okay, so we're trying to say our goal is are there k disjoint subsets? And disjoint means that they don't share a common element. So set 1 and set 2 are not disjoint because they both share the element B. And normally k will be some random value, so we can say k equals 2. Are there 2 disjoint subsets? Yes, because we can select subset 2 and 3, or we can do subset 1 and 3, and those will be a valid solution. So normally the output will be like yes or no. Yes or no, like, can we do this? Can we do our goal in a valid way? Okay, so let me move this up a little bit. Something that helped me was to draw this visual. I'm actually completely stealing this from my professor, but that's okay. So yeah, we have the universe, and these are all the elements in the universe, and then we also have our subsets. So 1, 2, 3, and then I'm just gonna map out the elements that each one. Whoa! Oh my goodness! Each ones that are contained in it. This should be B. Just can't write properly, I guess. Okay. Yeah. So this little visual we'll kind of use. So inputs for integer programming. There are normally variables. We're also given some constraints. And yeah, normally we're also given an objective, which is pretty much like the same thing as like our goal that we're trying to achieve. So how can we translate this? Well, we could say that each subset is a variable. So we're going to take our subsets, s of I, and we're going to translate this to x of I. So for integer programming, our variables are x of I. Okay, so what are some constraints that we need on our variables to make sense for set packing? Well, okay, we either include that subset or we don't. We can't include like half a set or like, I don't know, 2 of that set. That doesn't make sense. We can't do that. So I'm going to constrain it and say must be either 0 or 1. Okay, and then what is the other really crucial thing about set packing? We can't have sets that overlap with each other. They must be disjoint. So what I'm going to do is I'm going to look at each universe, so each element in our universe, goodness, and we'll say there's j elements, I swear I'm literate. Okay, and then, yeah, let's say there are n subsets. Okay, the way we can write this, a little mathy, but it's fun, I promise. For every single element, we want to iterate through our subsets. Okay. Let me write this first and then I'll explain. Okay, for every single element, we're going to look through x of I represents whether subset is included or not. And that's, we already know it's either going to be 0 or 1. What this means, this is supposed to be like the truth value. So it's either going to be 0 or 1, like for true or false. If j is in that particular subset, then I'm going to say like 1 it is, or 0 it's not. So yeah, it's basically saying that every selected set is pairwise disjoint from each other. Okay, so let me show an example given our lovely picture. So for every element in j, so I'm going to look at A first, the first one, and I'm going to look at every single set, and if the subset is included, okay, so for all j, so we're going to look at A, we're going to look at B, we're going to look at C, we're going to look at D. Okay, so let's say that for the 2 that are included, we're going to include, let's include A and B. Obviously this is not a valid solution, but let's show why this is not valid. Okay, so for A, this is me iterating through all my j. I want to look through each subset. So for subset 1, is the subset included? Yes. And then, is A included in that subset? Yes. We're looking at all of our other subsets. B, is it included? Yes. Does it include A? No. So our total sum equals 1. And that's perfect, because that fits our constraint. Okay, let's look at the element B in our universe. Okay, so an A, is A included? Yes. Or sorry, is S1 included? Yes. Is B in that subset? Yes. Okay, now looking at our second subset, is it included? Yes. Is this J element included? Is B included? Yes. And then I guess we also have to iterate through all of our subsets. Is this one included? No. Does it have B in it? No. Cool. So our total sum is 2. And this is really bad. So this would not fit our constraints. So this is properly returning. If we have a no instance of here, it's saying no as well. But let's show if we have a yes instance. Honestly, I just wanted to flex that I have erasable highlighters. Obviously, they don't work very well, but okay, no. So let's say the two that we chose were this one and this one. Okay. Let's draw a new thing. Our sum would look like this. Do we include it? Yes. Does it include A? Yes. Plus 0 times 0 plus 1 times 0 equals 1. Perfect. Okay, B. I'm just going to speed through this. Okay, so yeah, notice that all of these J values fit our constraint. They're less than or equal to 1. Really, they should either be 1 or 0, because this is integer programming. And then also, all of our subset values are either 1 or 0. So this is an instance of subpacking that also worked for integer programming. So yeah, that's pretty much it. That shows that we know that because we were able to create a valid translation, integer programming must be NP hard.